Yes.
Okay. Okay. Now, so my name is Antonio, and I am a PhD student at the Faculty of Physics of the Complutense University of Madrid, supervised by Marisa Montoya, which hasn't been able to be here now. So I'm giving the talk instead. My main focus of research in the PhD is about Antarctica, but I will talk a little bit about Greenland, touching some issues that have been done by other members of my group. So the outlook of the presentation will be something like this. I will start talking about the Greenland and Antarctic ice sheets and their influence in the climate. And also touching some feedbacks in relation with this ice sheet. And then I will focus on the Antarctic ice sheet, talking about the marine ice sheet instability and the sources of uncertainty related with this ice sheet. I would like to start my presentation with this figure, which is a representation of an ice sheet. Ice sheets are vast amount of ice, which are not isolated in our climate system. They have relation with other components of the climate system, like, for example, the ocean through currents, the atmosphere through precipitation and snow, and also with the lithosphere by geothermal heat fluxes and other interaction with the components. The 3 points that I want to mention about this ice sheet is that they have a huge albedo. That is to say that they have rebound most of the radiation that comes to them, so they have a lower temperature because of that. They have a huge elevation because all this amount of ice goes like 3 or 4 kilometers high, for example, in Antarctica. And this is also in relation with temperatures. But what is more important about them is the storage of fresh water that they have in its system, which has a relation with sea level. All these feedbacks, all these variables are in relation with some feedback, like the ice albedo, by which an increase in temperature will lead to an increase in melting. If we have more melting, more places of the ice sheet will be shown to the exterior, and therefore the albedo will be reduced. If the albedo is reduced, the temperature goes up. So we have a positive feedback with the albedo. The same happens with elevation. If the temperature goes up, we will have more melting. If we have more melting, the elevation of the ice sheet will reduce. And if we have a lower elevation, the temperature will increase. And therefore, we have also a positive feedback with elevation. And I will now show you in the current state of our climate, we have 2 ice sheets. One is the Antarctic ice sheet, which is in the south, and the Greenland ice sheet in the north. But in the past, there were other ice sheets in the planet, like the Laurentide ice sheet and the Scandinavian ice sheet that have disappeared. But what is important about these 2 remaining ice sheets is that both of them are losing a huge amount of mass of ice in the last decades. In these simulations, in this observation with the satellite grays, we can see that there is a loss of ice coming from the year 2002 until the year 2023, in which we can observe that for Greenland, all this reduction is happening in the margins of the ice sheet. Meanwhile, in Antarctica, all this ice loss is concentrated in the west region, especially in this region here, which is the Pine Island Glacier, in relation with the warmer waters that we are encountering here. There are many differences between Greenland and Antarctica. In fact, Greenland is 7 times, Antarctica is 7 times the size of Greenland in area, but Greenland, for example, contributes to a sea level. We contribute to a sea level rise in more than 7 meters if all the ice were melted, and Antarctica in more than 50 meters. Nevertheless, the rate at which they are losing mass is a little bit different, gaining Greenland. The mass, all this loss of ice is can be quantified mathematically by the variable known as mass balance, which is the difference between the accumulation, in which they intervene processes like snow, precipitation, and the redistribution of the ice in the ice sheet, and the ablation, which contains all the processes which leads to a leaf-up of ice, like calving, discharge, melting, and all the processes, all these kind of processes. And this mass balance could be quantified in mathematical terms with three variables: the surface mass balance, the basal melting, and the discharge. Basal melting and discharge contribute negatively to the mass balance, but surface mass balance could be positive or negative, and this has a profound influence in the rate at which we are losing mass. For Greenland, basal melting is almost neglected, and in recent times, 50% of the ice mass loss is due to discharge, and the other 50% to surface mass balance. In fact, we can see in this figure for the surface mass balance that some parts of the margins have a negative surface mass balance, and therefore this equation gives a negative term if we put this variable as negative. So for Greenland, the surface mass balance is the critical variable. Meanwhile, for Antarctica, we see in this map that surface mass balance is positive almost everywhere. So if this term is positive, the mass loss is due to the other two, which is basal melting and discharge. And Robinson et al. In 2012 make this simulation in which they demonstrated that Greenland has a tipping behavior in which there is a critical threshold between plus 0.8 and 3.2 degrees Celsius above pre-industrial, with most simulation putting the number in 1.6 degrees. And for Antarctica, Garve also demonstrated that there is an hysteresis cycle similar to the one that Robinson made for Greenland. And they found two critical thresholds. There is one between 1 and 2 degrees, which is relevant in short-term trend. In fact, 1 or 2 weeks ago, I think that we surpassed this threshold of 2 degrees in the planets for 1 or 2 days. And there is also a long-term threshold between 6 and 9 degrees, which could make the waves, the west part of Antarctica, known as waves, collapse, and even some parts of the East Antarctic, if we surpass this threshold. So from now on, I will try to focus on Antarctica and make a brief summary of the main results that we have found in our group in relation with this ice sheet. But before that, I will try to explain a little bit what is happening in Antarctica. Antarctica, if we take out all the ice in Antarctica, we will see something similar to this. We have a bedrock elevation that is above sea level in most of the East Antarctic part, with mountain ranges surpassing 3,000 meters, like the Transantarctic Mountains on the Carbon Mountains. But the curious thing about this plot is that the west part is almost entirely below sea level. And this has a strong influence in the sense that most sectors here are marine-based and has a strong connection with the ocean. If we look at the figure on the right, we see that surrounding all Antarctica, we have more than 300 ice shelves that I will show you later, that has a great influence in controlling the ice from the interior. And in these sectors here on the on the west, we see that there are two, which are the biggest one, which are the Ronde-Filner ice shelf and the Ross ice shelf, which has a size similar to Spain or France. The most important thing about this ice shelf is that they do not contribute to sea level directly, because all the ice that is in the ice shelf is already on the ocean. But they contribute indirectly by controlling the flow of ice coming from the grounded part, which is separated from the ice shelf by this transition region known as the grounding line. So if the ice shelf is debilitated, it could be destabilized, and all the ice coming from the interior could go to the ocean, and this will cause the sea level rise in the future. How can this ice shelf be debilitated? One of the main causes are that circumpolar water that is coming from other parts of the world could enter the cavities beneath the ice shelf and produce a retreat in the grounding line. This warm water that is entering here could debilitate the ice shelf and produce all the effects that I will show you now. So this leads to what is known as the grounding line feedback, by which a retreat is triggered here. If we consider a retrograde slope in which the ice sheet is based, and we have an intrusion of heated water, we can produce that the grounding line could retreat toward the interior. And as we are over a retrograde slope, the thickness in this part is increased, because now there are more difference between the surface elevation and the surface of the ice and the bedrock. Based on this equation obtained by Schuff in 2007, there is a proportional relation between the flux of ice in the grounding line and the thickness H here in this grounding line, which has a positive and bigger than 1 exponent. So if we trigger a retreat in the grounding line produced by heat water, we will have more thickness at this grounding line as it moves towards the interior, and it will cause the flux of ice to increase, which is represented by these black arrows. So this will lead to more discharge of ice, and in turn to more retreat. And this is a positive feedback again, which is in relation with the instability, which is the marine ice sheet instability, or MIST, that is particularly dangerous in the west part of Antarctica, which have some more regions of with a retrograde slope. Nevertheless, modeling this marine ice sheet instability is pretty difficult, because on one hand, we have the ice sheet, which is grounded, in which we have a vertical profile for the velocities of this ice, that looks like this. The parts the ice which is near the bedrock has a slower velocity, because it has a lot of friction with the bedrock. And as we move outwards, we see that the velocity is increased. Nevertheless, in the part that is floating, the ice shell, these velocities are almost equal in all the thickness of the ice. So there are some problems in modeling the transition region between one part and the other. But this comes in handy to talk about modeling. And this leads me to the second part of the presentation, in which I will talk about the uncertainty and its assessment. In our group in Madrid, we use an ice sheet model, which is Gelmo. It's a 3D thermomechanical ice sheet model that you can find for free in this GitHub repository with all the documentation. Gelmo is not the acronym for anything. It's just a mountain range in Madrid that is pretty similar in its form to the representation of an ice sheet, and that's why they decided to name it GELM. In the last report of the IPCC in 2021, they show sea level projections for the year 2100 and also for the year 2300. And what they show is that there is a great uncertainty in all the simulation, especially when considering the forcings. For example, for the year 2300, we see that choosing a low emission scenario like the SSP 1 2.6 leads to contribution between 0.5 and 3.5 meters, and using a high emission scenario like 8.5 leads for contribution between 2 and 7 meters. But as they say, 15 meters cannot be ruled out. So there is a great uncertainty in the quantification of the sea level projection. The sources of this uncertainty can be classified in two. One is the forcing on the scenarios, and the other is dependent on the model that we use. In this case, in our case, GEM, and is in relation with the dynamics of the ice. For example, basal friction or hydraulic could be part of this ice dynamics uncertainty. Ice-ocean interaction, which is the part in which I'm more focused in my PhD in relation with basal melting, and ice-land interaction, which is in relation with the glacial isostatic adjustment, and the ice-climate interaction, for which we will need fully coupled models. So in the rest of the presentation, I will try to give a summary of what we have done in order to assess this uncertainty with GEM. Starting with the first one, basal friction can be modeled mathematically by this relation in which basal stress is a function of the basal ice speed and the effective pressure of the ice. Normally, it is used a power law by which relates the basal stress with the effective pressure and the basal velocity in this way, using a parameter m. If m is equal 1, we have a linear law. If n is equal to 2 or 3, we have the Weirman type friction law. And if n goes to infinity, we have a plastic law. Nevertheless, using these laws has a problem in relation with the discontinuity in basal velocity and that it must put a limit to the basal stress. So it is often used as a solution, which is the regularized Coulomb law that you can see here in the dashed lines, and that is represented by this mathematical formulation. So in 2021, one of my colleagues in Madrid, Javi Blasco, that now is working in Belgium, and made simulations from the last glacial maximum to the present using the 4 different laws, from linear, power law, the regularized law, and the plastic law. In order to guess how the uncertainty can be assessed here. And he found that as he did the simulation, that you can see here that at the end of the period, there is a volume difference of more than 3 meters of sea level equivalent compared to observation. So using one law or the other can influence our results in our for the projection of sea level. In passing to the next source of uncertainty, the ice-ocean interaction, in which I am focused now. In fact, I am about to send my paper, and we have the process of basal melting. We contribute negatively to the mass balance, as I have shown you in one of the first slides. The problem here is to guess what is happening with the basal melt rates to run them on the grounding lines, because we don't have observation beneath the ice shelves because of the difficulty to collect them. So an offline approach that is often used is to consider the oceanic temperatures and variables that we had here due to other GCN models, and try to guess through a basal melting parametrization what is happening here. So we have the data here, and we try to guess what is happening here to a melting parametrization. There are different ways of parameterize this process, and I will try to give you now 3 of them, which are the more basic. One of them that we have used, but there are also other more complex. The first one, and more simple, is a linear relation which relates the thermal forcing in here with the basal melt rates in here through a parameter called the heat exchange velocity, gamma. However, this parameterization is pretty simple and do not consider other feedback that could be happening inside here because of the circulation of the waters in there. So a better approach is the quadratic parameterization. We consider the power of 2 of this thermal forcing on the ocean, and try to guess the basal melt rates, again through a parameter called the heat exchange velocity. But an improvement made by Jordan in 2020 is the quadratic non-local parameterization, because the linear and the quadratic that I have shown you on the previous slide only consider a local approach, in the sense that what happened in one particular cell of our domain only affect that particular cell. But it is demonstrated that in such sectors of Antarctica, what happened in one point could influence other points in that sector, which are connected by circulation. And in order to capture that, Jordan made this parameterization, which is also quadratic, but it considered temperature corrections over each sector of the 18 in which Antarctica is divided. So we decided to take this parameterization, which is also used for the Isthmic Seas intercomparison project, and we decided to make simulation with 3 different values for gamma 0, the parameter which is controlling this transition between the thermal forcing of the ocean and the basal melt rate. These values are 3. One is 9,620, 14,500, and 21,000 in the low, medium, and high value. At the same time, I have also said that another source of uncertainty, not related with the model that we are using directly, is the forcing. So we decided to test both the uncertainty on the forcing and on the basal melting parameterization. In order to test the sensitivity and uncertainty in the climatic forcing, we selected 5 experiments from the Isthmic Seas 2300 protocol. 4 of them are high emission scenarios from CIMI-5 and CIMIC Seas, and there is also another low emission scenario. Their force, the armor phase forcing, is put in this figure on the top panel. We can see that we have the 5 models are CCSM4, HAPGEN, SSN2, UKSM with high emission, and UKSM1 with low emission. As we only have data until 2300, we decided to extend the simulation until 2500 by choosing the average climatology of the last 10 years of the period. So this is after 2300, we keep a constant climate. The most important thing about this is the difference for 2 of the models in terms of atmospheric and oceanic forcing. For CCSM4 and UKSM with high emission, the blue and orange curves, we have a pretty similar atmospheric forcing, but in terms of oceanic forcing, they differ in more than 2 meters at the end of the period. And this will have important consequences in terms of sea level, as I will be showing you now. These are the sea level projection with testing the uncertainty in the forcing and in ice-ocean interaction with basalt melting with this parameterization from your time. And we can see that sea level rise at 2500 could reach 3.5 meters in the worst case, which is for the forcing coming from 2002 Wakam. But what is interesting about this plot, in which the shade represents the spread produced by the values of the gamma zero parameter, is that the difference between the models UKSM1 and CCSM4, based on what I have just said, their curves does not intersect even with the shadows. And this is due because of the oceanic forcing, because they had a similar, coming back to the previous slide, they had that very similar atmospheric forcing. So the only part which is causing the difference here in sea level contribution is the behavior of the oceanic forcing. In terms of sea level rate, we can see that there is an increase of the rate until they, in all the models, until they reach the GR 2300, in which that rate, as we are keeping constant the climate from that date, and there is a reduction in the rate, but it continues to lose mass, but at a lower rate. Separating this contribution in the two main regions, the West Antarctic part or waves and the East Antarctic part, ACE, we can attribute the sea level contribution for Antarctica to the West Antarctic part, with contribution of more than 2.6 meters for the worst case. Meanwhile, the East Antarctic part has some experiment in which the contribution is negative, for example, for CCSM4. So they have a reduction in sea level. So the East part always tries to counterbalance what happens in the West Antarctic part, which is the main source of uncertainty, as we can see in the shadows, which are pretty reduced in the East. In terms of 2D, we can also see this behavior observed in the time series. And we see the evolution from 2100 to 2500 for the different UCM models. We can see that there is a retreat in the grounding line represented by dashed lines here toward the interior in the worst cases, like for example, Session 2. We see that as we move to the right in this row, this retreat is being more and more, is migrating towards the interior, because the red colors here represent a loss of ice, while the blue color represent a gain in ice. We can also observe that in the interior of and in the east part, almost everything turns blue. This is due to, because in a warmer climate, we would expect more precipitation, and this precipitation will accumulate in the interior. Comparing the two experiments in which we had a similar atmospheric forcing but a diverging oceanic one, CCSM4 and UKSM, both with high emission scenario, we can see in the simulation that there is a great difference in terms of the timing of the loss of ice. UKSM1 starts to lose all the ice in red here as soon as in 2150. But for CCSM4, this rate is slower. It ends up losing a lot of ice in the west, but is at a different rate compared with UKSM1. Based on this characterization of the atmosphere and the ocean, we decided to implement new simulation, neglecting one component of the other. So in this left panel, we see the sea level contribution when only the atmosphere is being considered. So the ocean here is kept constant with the same values of the start of the simulation, which is in 2015. Meanwhile, in this plot, we see the contribution when only the ocean is considered. So here the atmosphere is neglected. And we can see that there is a huge difference in both plots. So when the ocean is not acting, the atmosphere will have a positive impact in terms of sea level because it's decreasing here in some of the experiments, including UKSN1, and only in 2 of them could contribute positively, but with numbers around 1 meter. But for the ocean only experiments, we can see that there is a huge uncertainty because of the shade here, and all the experiments produce positive contribution in terms of sea level. We also have decided recently to produce branching off experiments, extending the simulation more until the year 3000, and considering a stopping of the forcing at different year. So in this column here is represented the year we stop the forcing: 2050, 2100, 2125, 2150, 2200, and 2300. From that year and until the year 3000, we kept a constant climate with the average of the last 10 years. So we can see, what we can guess from these plots is that if we stop the climate and the forcing before 2125, we can achieve that at the end of the period in 3000, the grounding lines in the main ice shelves has not retreated a lot. But if we surpass the year 2150, we can observe that at the end of the period, the grounding line has migrated many kilometers toward the interior. And if we continue the simulation, stopping the climate at 2300, we can see that the West Antarctic part has almost collapsed in these red colors. It can also be observed in terms of time series, considering the different stopping points that we have selected. We see that before the year 2125, in this blue color, the sea level contribution at year 3000 does not surpass 1 meter, but if we pass and stop the forcing in 2150, this sea level contribution could go from 1.5 meters until even 5 meters. So there are important consequences on whether stopping the forcing at 1 year or not. The large source of uncertainty that I want to talk about is the interaction between ice and land in the ice sheet. Because all I have been talking about until now is in relation with atmosphere and ocean, which is over surface. But below the surface, there are also processes happening in an ice sheet. There are subglacial volcanism, which is particularly important in the West Antarctic ice sheet. There is also a variable basal hill flux, and this could influence the way in which it could affect the ice dynamics of the entire ice sheet. One particular process that is in relation with this loss of ice is what is called the glacial isostatic adjustment. If we have an ice sheet and we remove it, we would expect the lithosphere to recover and produce an uplift of the bedrock. So this has a strong influence on sea level, because if we move the bedrock upwards, sea level will decrease, and there are some important parts in Scandinavia where the ice sheet was removed 13,000 years ago or so, where the floor is being elevated at a rate of 8 millimeters per year. This process is very difficult to model, but one of my colleagues in Madrid, Jan Jerexen, has developed a model in Julia, which is called fast isostasy, that is being incorporated in Gelmo by Marisa now, and and the objective here is to have a model in order to test the sensitivity and the uncertainty that is being produced by the lift of the West Antarctic part it loses the ice. Because if we lose the ice, as I have said before, the lithosphere is bound to elevate itself, and it could influence the simulation and projection of sea level. One last point that I want to mention is the ice-climate interaction, because the climate system is composed of ocean, cryosphere, atmosphere, lithosphere, and biosphere, and all the components are related. But when we make the simulation, we consider them separately. And one way to improve our assessment of uncertainty will be in the future with couple models that consider everything together. And one of them is ClimberX, in which Gelmo is participating, and that in the coming years could be a good tool to use to assess all this uncertainty. So as conclusion, I want to point out that there are positive feedbacks in relation with ice sheet that are pretty important for the climate, like the ice albedo, ice melting, the melt elevation, I think, and also the ground line feedback, which has the potential for irreversibility in some parts of Antarctica, like the west, where the messy marine instability could be triggered. But there are also many sources of uncertainty. I have shown you 5 here that has been addressed by my group in Antarctica. But in the future, it will be a good tool to use a couple models and see how they simulate and project everything joined together. This is all. Thank you for your attention.